Everyone, welcome to this video, the first in a series about the analysis of N-of-1 trials. These videos go along with the self-study assignment in which you will be diving into the world of Bayesian analysis. The learning goals for the series and the self-study assignment are that you can explain how studies to evaluate treatment effects in rare kidney disease are conducted. So to that end, you need to be able to interpret the results of an N-of-1 trial. You need to be able to explain what a prior probability or prior density is, what a likelihood function is, and what the posterior density or the posterior probability is. You can also explain a little bit the difference between Bayesian and frequentist statistics, and you understand some of the basic concepts underpinning Bayesian statistics. And the latter two is what we will be discussing in this first video. So understanding the basic concepts of Bayesian statistics and the difference between Bayesian and frequentist, which is what you've been learning thus far in the curriculum. To give you a very brief overview of statistics in the last 150 years or so, most approaches have been frequentist, even though the Bayesian approach is actually somewhat older. You've met the frequentist approach and know it as statistics today, where basically the way you deal with a scientific question is that you make an hypothesis. So for instance, treatment A is better to achieve a lower blood pressure than treatment B, and then you reverse this into what we call a null hypothesis, which is basically not saying treatment A is better than B, but it's saying treatment A and B are have a similar effect, which is the null hypothesis. There is no difference. Then you pick a model. For instance, we decide to compare the mean blood pressures between the groups treated with A and B. We collect some data, and we determine the probability of the observed blood pressure, or the difference in mean blood pressures, under the null hypothesis. This then gives us a p-value, and we make a decision based on that p-value. The notable thing here is this introduction of a null hypothesis. We're not actually targeting the thing that we want to know, which is treatment A, is it better than treatment B to get a lower blood pressure, for instance, but we're answering a different sort of question, which is saying there is no difference between treatment A and B in getting blood pressure. If there is a difference, then there's a probability that this difference still fits the null hypothesis, so that there is no difference. So this is a little bit of a, well, scientific sidestep, which we really don't want to make, actually. We just want to know whether treatment A is better than B, right? But, well, we can't really tell with a frequentist approach. With the Bayesian approach, we sort of take a similar mindset. We make this hypothesis, treatment A is better than B, and we use it to generate some prior distribution, some prior ideas about how blood pressure may be distributed. So for instance, we can say blood pressure is a normally distributed variable. Then we pick a model and we say, okay, for normally distributed variables, we can compare the means, which is similar to the frequentist approach. We collect some data and we combine the prior with the data and to generate a posterior distribution. So knowing that we have a mean, expecting this kind of range of blood pressure, we add some data and then we generate a posterior. Afterwards, we can interrogate this posterior and ask questions like, what's the probability that blood pressure under treatment A will be lower than under treatment B? To me, at least, this latter approach makes more sense. The only difficult thing about this is that from a frequentist tradition, in which I've been schooled myself, this idea of prior and posterior distributions is a little bit vague. And that's what this lecture will go into a little bit more, to try and take away a little bit of the mysticism or the vagaries that are sometimes associated with Bayesian statistics. So there are three fundamental concepts for Bayesian analysis. One thing is called, that's something that you'll encounter a lot when talking about Bayesian, is a prior distribution. And this is nothing more or less than the assumed distribution of a variable before we've seen any of the data. So it's actually an unmeasured variable. This prior distribution may be, for instance, the distribution of height among all of the students following this course, where I could say, okay, I think that your heights are all together are normally distributed, that the average is 175 centimeters, and that it ranges between, let's say, 155 centimeters and 195 centimeters. I might be off, I might be pretty close, but that's basically how you think up a prior. And that's all that there is to a prior distribution. It's an assumed distribution before I've actually measured all of the data. I have never measured your heights and still came up with this distribution. Then there's something called the likelihood function, which is the statistical machine that combines data and priors. So what the likelihood function in this example of heights was, is the normal distribution. So for the likelihood to generate a normal distribution, you need to know a mean, you need to know a standard deviation, and then you can put in data and you can estimate this mean and you can estimate the standard deviation. This prior combined with the likelihood function and the data can be used to generate a posterior distribution. If I started measuring your heights, I might find out that in fact, after a couple of observations, your mean may be a little bit higher than the 175 centimeters. It may be 180 centimeters. The variation may be a little bit lower than somewhere between 155 and 195 centimeters, right? But that's something that you can learn of the data, and with the likelihood function and the prior distribution, you end up at the posterior distribution. Funny thing is that this posterior distribution can then be turned into a prior distribution. We collect some more data and we get a new posterior distribution. So this is something that's called, this cyclical approach is something that's called Bayesian updating. And this is a nice attribute of Bayesian statistics. It doesn't punish you for getting more data. In fact, your estimates become better if you get more relevant data. So how do you choose the likelihood function? I've talked a little bit about height, where there's something that's called the normal distribution, which you may be familiar with. A normal distribution may look something like this. And this is a normal distribution for a mean value of 0 and a standard deviation of 0, which is actually not possible, so it probably defaulted to its standard of 0.5. So this is a normal distribution for a mean of 1 and an SD of 0.5, looks like. Another distribution that you may be familiar with is the binomial distribution. And this is actually something that arises, for instance, when you toss a coin. And that's what's happened here. So this says the probability of 0.5, which is a coin toss. You've got 50% times 50% of the times you've got heads, 50% of the times you've got tails. We've done this coin toss 10 times in a row, and then we count up the number of the times that you've got heads. If you do this 1,000 times over, you get a distribution like this, where in a very few cases you may have seen 10 times heads, in very few cases you may have seen 10 times tails. Most of the times you'll see 5 times head, 5 times tails, and that's what you see here, the tip of the distribution. And then there's one that you might encounter also quite often in medical science. That's something called the exponential distribution. And this is something where the real values, or the values that you can observe, are somewhere between 0 and infinite. And this is something that you see in lab values, for instance. Like your blood glucose, it will never be 0, because if it's 0, you're dead, and it may take a very high level, something like 20. But for most people, it will be lower. And so blood glucose is something that you would expect to follow a exponential distribution, which is something that you see here. So these distributions are chosen based off of what you expect your outcome to look like. If it's something like height, which has a mean that's very far away from the 0, and it has a finite variance, it will look like a normal distribution, which you will encounter a lot. If you know that there's a sort of a coin tossing problem, where someone is alive or dead, healthy or diseased, then you will see the binomial distribution. And if you know it's something like a lab value that ranges between 0 and infinite, it might be an exponential distribution, right? So that's how you choose the likelihood function. Now, how do you choose priors? Priors you choose basically off of common sense and substantive knowledge. So you might choose it based on the possible range of the outcomes or the data generating process, which is similar to the distribution that we saw before. And there may be some statistical reasons. What we often use and see in Bayesian statistics are something that's called weakly informative priors. And a weakly informative prior basically restricts the value of the data to a realistic range to keep a model in check. If you use no prior at all, your model will go wild if it sees a very rare observation. It will produce very strange and esoteric estimates. Whereas if you use a prior, then you may get this wild observation, this completely out there, but it won't shift the posterior a lot. So it won't change your view of the world a lot, or the model's view of the world, better said. Only if you get a lot more data, then the model will start to shift, and it will start to change its view of the world. And this is something good, right? So if you make extraordinary claims, you need extraordinary evidence, and this is basically a way to get this into a statistical model. One big piece of advice is always to plot your priors, run a model, and check the posterior. In Bayesian statistics, you can check the model if it works technically, if it's technically sound, even before you've seen any of the data. You can still produce results, you can still check if your model runs as expected. Then you add some data, and you get some real answers, which you know you can trust. And that's a nice thing about Bayesian statistics. So this is a Bayesian model in action. It's something that you will be producing during this assignment, where there are 3 treatments: gluconate, aspartate, and lactate. The details you've seen in the article, and you will also see in the assignment. And where basically the one lactate achieves a higher concentration of magnesium in serum versus the magnesium gluconate. Here on the right hand side, you see something that's really cool about these posteriors, because these are posteriors after we've chosen the priors, added the data, run the model. These are the posteriors. And this is something that you can do with the Bayesian posteriors, with the posterior distributions. You can subtract them from each other. So we can subtract from the posterior distribution for magnesium lactate the posterior distribution for magnesium aspartate in blue. And so for each element in this distribution, you subtract a similar element for that distribution, and you get a new distribution, which is the difference, and it's shown here in our code. And so you see, I've colored here all of the results that are below 1, where the magnesium concentration for the aspartate is lower than the lactate, and you can count the number of times that this difference is lower than 0, which is basically what's done here. You divide it by all of the observations, so there are 10,000 observations here, so you count the number of times that the difference is lower than 0, you divide it by 10,000, and you get a probability. And here you're saying there's a 97% chance that the magnesium concentration will be lower when you use aspartate compared to lactate. Bam, that's your answer. And that's actually a substantive answer. There's no p-values here. This is just the answer, period. So in summary, to perform Bayesian data analysis, you need to define a model for the outcome, which requires us to make some assumptions about the distributional outcome. Is it normal? Is it a coin toss? Is it something that ranges between 0 and infinite? You formulate some relation between the variables of the model, which we'll dive on a little bit deeper, but this is similar to frequentist statistics actually. You need to assume some priors for each variable, and for this you use basically common sense or what you know already. You use some approximation, which is very technical and we won't go into. We'll see that in the next videos. and then we sample the posterior and ask the model questions, like we did in the previous slide. Now, this may seem like a little bit of black magic to you right now. Don't worry, we'll be diving into R code soon, and we'll be going over each step to make sure that you know what's actually going on before you try it yourself. So thank you for watching, and see you in the next video.